So, we're going to tackle a pretty fascinating scientific puzzle today. How do you get two things that, well, they just don't want to mix to become one? We're diving into the secret of unmixing the unmixable. Let's get into it. You know how some things just don't get along, right? Like oil and water. You shake them up and, nope, they separate every time. But what if there was a hidden rule, a secret switch you could flip that changes everything? Could you actually force them to mix? Well, the answer is yeah, kinda. For certain mixtures, there's this secret tipping point. It's a moment where all the rules of separation just break down, and suddenly two totally different liquids become one. And that's what we're after today, finding that exact point. All right, so our story starts, like any good mystery, with the key players. And this puzzle is all about a very, very particular pair of liquids. Okay, first up, a quick term we're going to need, a binary mixture. Sounds fancy, but all it means is a system with two different liquids. Sometimes they mix perfectly, like water and alcohol, but other times they don't. And that right there is where it gets interesting. So let's meet our two main characters. In one corner, we've got good old water, H2O, we all know it. And in the other corner, something called phenol. It's an organic compound that actually starts out as a solid crystal, but then it melts into a liquid. These are the two we're trying to get to play nice. And here's the problem. When you try to mix these two, they just don't fully cooperate. Scientists have a term for this, partially miscible. What you get is this cloudy, hazy mess, which is basically the mixture's way of telling you, nope, we haven't become one yet. So that brings us right back to the big question. Is there some way to break down that barrier? Can we turn that cloudy, separated stuff into one single, perfectly clear liquid? To figure this out, we've got to follow the clues. And for that, we're heading into the lab to see how a researcher tackled this exact problem. All right, so researcher Hiba Zara took this on. Her plan was to solve this puzzle by tracking two really specific things about the mixture while she tweaked the conditions, its viscosity and its electrical conductivity. These were going to be her clues. So what exactly are these clues? Well, viscosity, that's just a fancy word for how syrupy a liquid is. Its resistance to flowing. Think about molasses compared to water. Molasses has high viscosity. Then you've got electrical conductivity, which is pretty much what it sounds like. How well can this liquid carry an electric current? That all comes down to how well tiny charged particles, or ions, can move around inside it. Okay, so this is one of the key tools in her arsenal. To measure that syrupiness or viscosity, she used this thing, a glass viscometer. It looks simple, but it's super precise. Basically, she timed how long it took for the liquid to flow between two little marks. That gave her an incredibly accurate measurement. And for the second clue, she used this guy, a conductivity meter. This device just measures the electrical properties of the solution. It gives her a direct number for how well those little ions are moving around. So, armed with these two tools, she was ready to go hunting for that magic tipping point. All right, the hunt is on. The mission? Find that one single specific set of conditions where water and phenol finally give up the fight and merge into one. And the process had to be super methodical. First, she made a whole bunch of different samples, each one with a slightly different ratio of phenol to water. Then, each one goes into this super accurate temperature bath. The key here was patience. Slowly, degree by degree, she'd raise the heat. And at every single step, she'd take those crucial measurements, just watching and waiting for something to change. And then, as the temperature starts climbing past 50, then 60 degrees Celsius, something starts to happen. You can see it. That cloudy, murky look, the sign that the two liquids are still fighting, it starts to soften. It begins to fade. And then it happens. The aha moment. This is where all that careful, patient measurement pays off in one single incredible instant. The first piece of the puzzle is the temperature. It's not 66, it's not 68. The magic number is exactly 67.0 degrees Celsius. And the second piece of the puzzle? The concentration. The mixture has to be precisely 33.90% phenol. A little more, a little less, and the whole thing doesn't work. But when you hit both of those numbers at the exact same time, that precise temperature and that precise concentration, bam! The cloudy solution just vanishes. Instantly, it becomes perfectly clear. Water and phenol aren't two separate things anymore. They are completely, totally mixed. They've become one. So this incredible moment has a name. It's called the critical point. It is that one-of-a-kind combination of temperature and concentration where a mixture that shouldn't mix suddenly becomes totally uniform. It really is a tipping point in the physics of how liquids behave. Okay, so we found the critical point. Awesome. But what does it all mean? Well, this is where those original clues, viscosity and conductivity, come back into the picture. They're going to tell us about the brand new liquid we just created. To figure out what's going on, scientists use a special chart called a Walden plot. It basically maps conductivity against viscosity to see how easily those charged ions can move around. Now, that straight diagonal line you see, that's like the gold standard. That's a perfect ionic liquid, where everything is flowing freely, no problem at all. So, the big question is, where does our new water-phenol mix land on this chart? Well, the data showed it falls below that ideal line. This gives it a classification. It's a poor ionic mixture. What that really means is, even though the water and phenol have finally mixed, they're still kind of clinging to each other. Those charged particles just can't move around as freely as they want to. It makes the new liquid a pretty inefficient electrical conductor compared to an ideal one. You could say it's got its own unique and slightly stubborn personality. And all this leaves us with a pretty cool final thought, doesn't it? We just unlocked a hidden property in a simple mixture, all by changing the temperature. It really makes you wonder, what other secrets are hiding in all the everyday materials around us, just waiting for the right push, the right temperature, the right pressure to be revealed?